Hi everyone, I'm not wearing any pants. In this video I'm going to talk about what the composition of detrital sediment can tell you about source areas. Um, Detrital sediment is sediment that is eroded from a source and then transported and deposited in a sedimentary basin. The biggest factor governing the composition of detrital sediment is the composition of the source. Detrital sediment rich in quartz, like the one shown here, must have either been derived from a quartz-rich source or maybe has been enriched in quartz due to weathering during transport or multiple episodes of recycling. And we would call this quartz-rich sand here a super mature sand. Okay, well, just as a reminder, detrital sediment is classified on the basis of texture and composition, just like all rocks are. These ternary diagrams classify detrital sediment on the basis of the grain size, and the basic names we apply to detrital sediment and sedimentary rocks, such as gravel, conglomerate, sand, sandstone, mud, and mudstone, are based on grain size. Grain size is related to composition, however, because gravel clasts are big enough that they always retain the character of the original rock, no matter how coarse-grained that rock was. Sand, on the other hand, may contain some single mineral grains or fragments of fine-grained rock, and mud contains only small mineral fragments from the source and then clay minerals that are products of weathering. Because gravel is made entirely of rock fragments and not single minerals, we can classify gravels on the basis of the major types of rock fragments that they contain. A polymicted conglomerate contains many different types of rock fragments, and most conglomerates are polymicted. An oligomicted conglomerate, on the other hand, contains only one type of rock fragment, or a vast majority of only one type of rock fragment. When conglomerate is polymicted, classifying it can be complicated, so it's best to just describe the types of class in a given conglomerate that a given conglomerate contains and their proportions in order to characterize the source. So here's an example of that. This polymicted conglomerate contains a few class of what look like, let's say, granite, a few class of what looks like, say, volcanic rock, maybe andesite. A couple of things that look as though they might have been sandstones. And by going through and looking at all the different class types that occur in here, you can get a pretty good sense of what the source looked like for this gravel. And the best way to do this would be to superimpose some sort of regular grid over the conglomerate, like so. And in the outcrop, we can use something like a volleyball net. And then just simply count what type of clast you hit at each node of the grid. And depending on how accurate and precise you want to be, you might count 100 clasts, you might count 1,000 clasts, and this would give you a very good sense of what the composition of the conglomerate is. And we'd have a very good idea of the relative proportions of each type of class that make up the conglomerate. And this is going to give us a good idea of the nature of the source. Well, it turns out that if you apply this procedure to a stack of conglomerate, what you often find is that the history of erosion in the source area is preserved in the class types that occur at different levels in a conglomerate deposit. So let's take an example where we have a source consisting of rock type 1 overlain by rock type 2 and overlain by rock type 3. Well, if we begin to uplift this and erode it into a basin, the first thing to erode will be rock type 3 class of rock type 3 will be concentrated towards the bottom of what's being deposited as conglomerate. As you uplift this even further and erode down into it, then pretty soon you'll have source rock 2 exposed, and then erosion will produce class of source rock 2 towards the middle of the conglomerate deposit. And then finally, as you get eroding deeply into the source and you expose rock type 1, then class of rock type 1 will be eroded and deposited high in the sequence of conglomerate. Now what this looks like in real life might be something like this. You might have a major fault that's uplifting these 3 different types of rock, and erosion is going to strip off the uppermost one first, and as it erodes even deeper, it'll strip down into lower and lower levels. You'll always get a mixture, though, of all 3 types of conglomerate, or all 3 types of clast, and depending on how you uplift this, whether 3 sits on top of 2 and 1, or whether 3, 2, and 1 are exposed together as shown here, will affect how those clasts mix in the depositional basin. So this process here is called an unroofing sequence. Basically, you have an ordered stack of rocks in the source, and you get class types that are stacked in reverse order in the basin. Here's an example of an unroofing sequence from my research. This is from my PhD dissertation. A conglomerate that's about 1.5 kilometers thick is overridden by a thrust that carries dolostone, overlain by a little bit of shale with some diabase sills, and overlain by limestone. So we've basically got dolostone on the bottom, limestone on the top, and some other lithologies in between. Well, this, when we plot the varying proportions of dolostone to limestone clasts upward through this conglomerate deposit, what we find is that we have mostly limestone near the bottom, and as we go upwards, the proportion of limestone decreases and we have mostly dolostone. That indicates that the conglomerate was derived from the unroofing of this stack of rock, and because this stack of rock is what occurs in the hanging wall of a nearby thrust, this is a great way to tie sedimentary deposits to the uplift of a particular fault block. Sandstones are a different beast because they consist of rock fragments and individual mineral grains, not all just rock fragments. And the mineral grains that are most abundant are those that are most common in crustal rocks and most resistant to weathering. You may recall that sandstones are classified on the basis of quartz, feldspar, and rock fragments or lithics, and on the abundance of mud matrix. Quartz is the most stable to weathering. Feldspar is variably stable, but the most abundant mineral in primary igneous continental crust. And rock fragments have varying degrees of stability depending on their composition. And the clay minerals that form most of the mud are a product of weathering. Let's think about what types of sources might produce these different types of sand. So let's consider first a block of continental crust that begins to rift apart. Along the shoulders of the rift, you're uplifting crystalline basement rocks from the continent. And these are acting as sources, and the sediment eroded from those rift shoulders is getting deposited inside the rift. At some later time, this block of crust may rift entirely away, leaving you with an open ocean basin and a passive margin that's facing it. The block of crust adjacent to this passive margin is a craton, And since cratons are tectonically stable, any uplift that might supply sediment to this passive margin is going to be pretty far away, pretty far off to the left, maybe the other side of the continent. So this passive margin, at some later time, might be next to an ocean basin that is beginning to close due to subduction. Now we've got a trench, an accretionary prism, a forearc basin, and a volcanic arc sitting above that subduction zone. And finally, if we continue to close this ocean basin, the arc, forearc, trench, and accretionary prism are going to collide with that passive margin and take this whole series of rock and basically pile it up and fold it into a fold thrust belt. That's going to load down the crust, and you'll get a foreland basin next to it, and the fold thrust belt will then be the source for the sediment in that foreland basin. So each of these settings have very different provenance, meaning that the sediment has a different type of source. What do the sources for red numbers 1 through 4 look like? What type of sands would be produced there? Well, let's take a look at that. Let's just quickly draw a ternary diagram and then plot on it what we would expect for these different types of settings. In the first case, we are uplifting crystalline basement of the continental crust. That's going to consist of rocks like granite and maybe gneiss that are coarsely crystalline, and when you weather and erode those into sand, you're going to be producing large crystals, crystals larger than a grain of sand, of quartz and feldspar. So mainly what you're going to see in a situation like that is you're going to see compositions that are going to fall somewhere in this range for setting 1. And that would be a basement uplift type of setting. In our passive margin, we said that the source for any sand that ends up getting deposited here is going to be pretty far away because you're right next to a stable craton. There's no erosion taking place here, only transport of sediment. And the source for this might be some mountain range thousands of miles away in this direction. So you might have large rivers that are carrying sand a long way to get out here, and along the way that sand will be temporarily deposited in soils and so forth. And so by the time it gets out here, it's going to be pretty strongly weathered. And we know that of all the minerals that occur in sands, the most resistant to weathering is going to be quartz. And so we might expect that our sands in a passive margin next to a craton might be pretty quartz rich. Well, let's now look at situation number 3. In a forearc basin, we are deriving virtually all of our sediment from a volcanic arc. And since volcanic arcs are made of volcanic rocks, and because volcanic rocks are generally fine-grained, and their most common phenocryst is feldspar, what we would expect is that we're mostly producing rock fragments with perhaps a little bit of feldspar. And so situation 3 might end up occupying this realm, pretty quartz poor, with a lot of rock fragments and a fair amount of feldspar. Finally, when we collide the extinct arc with the continental crust and we uplift that old passive margin, what we're doing is we're uplifting a bunch of rocks that are sedimentary in nature and were quartz rich to begin with. And During this collision, we're very likely to metamorphose some of those rocks as well, and so we'll be uplifting some metamorphic rocks here too. Well, fine-grained metamorphic rocks will tend to produce things like fragments of slate, rock fragments of slate and perhaps schist and perhaps phyllite that all form rock fragments. Because these rocks were quartz rich to begin with, we'd expect to see a fair amount of quartz, and we'd expect to also see a fair amount of chert as well, if there's any chert in these sedimentary rocks. So we would expect that with mainly quartz and rock fragments, our setting 4 I would plot something like over here. What you're looking at here on the left is an empirical plot of North American sandstones in relation to their tectonic setting. This is from a series of papers by Dickinson et al. This one's in 1983. So this is an empirical plot of what all that stuff looks like. On the leftmost ternary diagram, instead of rock names, we have provenance types plotted on it. Here's the basement uplift field. Here's the craton interior field. And these provenance types are source types. Undissected arc, transitional arc, dissected arc. This would be a volcanic arc that still has its volcanic rocks. This would be one that's eroded more deeply into the continental crust or other crust beneath it. The recycled orogenic field basically refers to sediment that's been recycled from older sedimentary rocks, and so forth. So this looks pretty much like what we did on the previous slide. Continental block provenances, recycled origin provenances, and some sort of magmatic arc provenance. In order to properly measure the various types of sand grains that actually occur in a given sandstone, you really have to look at it under a microscope. So down at the bottom of this slide, I have 3 pictures taken down the barrel of a microscope. The image on the left shows a volcanic rock fragment, and what that looks like, I'll just outline it for you. So that's one single grain of sand, and you can see inside that volcanic rock fragment are lots of phenocrysts of maybe amphibole and plagioclase and so forth. Surrounding that volcanic rock fragment, you can pick out some single crystal grains of quartz. Some of those single crystal grains of quartz have undulatory extinction, and that is typical of quartz that has been strained by metamorphism. In the middle here, we see a single sand grain that consists of many individual crystals, all of quartz. And this would be a polycrystalline quartz grain symbolized by QP. This one here, another single crystal grain of quartz. And this would be a monocrystalline quartz grain. Here on the right, we have another monocrystalline grain of quartz. And it sits right next to boundaries of this are kind of hard to see. A grain of chert. Very fine grained polycrystalline quartz. There's another one right there. And some of these other things, what do you suppose that is? If you guessed rock fragment, you were right. So we'll call that L for lithic. Here's another QM. Rock fragment there, another volcanic rock fragment. So you can pick out a lot of these things underneath the microscope, but you really need a microscope to do it. The difference between this plot this one is that you see from what I did down here that there are many different types of quartz. Quartz can be monocrystalline, in other words, a single sand grain consists of just one crystal of quartz, or it can be polycrystalline. One single sand grain consists of numerous crystals of quartz, or it can be chert, which is just fine-grained silica. In the leftmost plot, we are counting monocrystalline, polycrystalline, and chert all as quartz. In the rightmost diagram, what we're doing is we're just counting monocrystalline quartz as quartz, and we're counting polycrystalline quartz and chert as rock fragments, which is pretty much what they are. Polycrystalline quartz is commonly eroded from things like schist and gneiss. Chert is eroded from a stack of sedimentary rocks. Chert usually occurs in limestones and so forth. Okay, so with those diagrams and with careful counting of sandstones and sand grains underneath the microscope, you can figure out what type of provenance your sand came from, whether it maybe came from a recycled orogenic provenance, a basement uplift, a craton interior, or a volcanic arc. It turns out that unroofing sequences can be recorded in the composition of sandstones too. So, for example, if you have a volcanic arc that is uplifted and eroded away, that uplift, initially, you may have volcanic rocks exposed to the surface, and that's going to produce mainly rock fragments. But as you uplift a volcanic arc, you're going to tend to get more and more quartz and more feldspar as you reach more deeply into the plutonic roots of the volcanic arc. So you'll trend from a true arc provenance into something that looks more like a basement uplift provenance over time, because you're eroding away the volcanic rocks on top of all the crystalline igneous rocks beneath it. So that's a common type of unroofing sequence that you see in sandstones related to volcanic arc. And how you'd recognize that under the microscope is you see here on the left a sandstone that consists mainly of volcanic rock fragments. I'll just outline a few of those. These are all volcanic rock fragments. A little bit of quartz. There's a quartz crystal right there, and that's polycrystalline. A little bit of plagioclase, and you can see the striations in that grain. And a little bit of monocrystalline quartz. But by and large, most of the sand grains in here are rock fragments, and I'll just outline a couple more of those. In the middle here, you see what feldspar looks like under the microscope. This is a grain of plagioclase. You can see the twinning that produces the striations in that plagioclase. And then on the right is a sandstone that is mostly quartz. So as you go from an undissected arc provenance, you might start with something that looks like this. And as you head up this unroofing trend towards basement uplift, you may start to see things that are more like a mixture between these two. A lot of quartz and a lot of feldspar. Okay, it's also possible to determine the provenance of sandstones from the composition and chemistry of common accessory minerals in sandstone. So not just quartz and feldspar, but other minerals that are sparse but still common in sandstones. By far the most useful of these is the mineral zircon, which is an igneous mineral containing large amounts of the radioactive element uranium. Uranium decays over time to lead, and by measuring the relative proportions of certain isotopes of uranium and lead in a zircon, one can determine the age of the crystal, and thus the age of the igneous rock from which it was derived. Zircons are as durable as quartz, which means they can be eroded from a source, deposited in a sediment, and then recycled numerous times into other sediments and sedimentary rocks. If you separate out a population of zircon from a sandstone sample, so you take a sandstone like this and you separate out maybe 1,000 zircons from that sandstone, and the procedure for doing this is pretty complicated. I won't go into it here, but it can be done. Once you've separated out those zircons, it's possible using modern methods to date each crystal separately, even though each crystal is only about 100 microns long. So that's about 1/10 of a millimeter long from there to there. These are all very fine sand. Using a 30 micron laser beam, we can drill a spot into those crystals. So what you do is you mount the crystals in epoxy, you grind them down so that their centers are showing, and then you zap them with a laser. We drill a pit into each crystal and we extract its constituent atoms into a mass spectrometer, which measures the relative proportions of uranium-238, lead-206, and lead-207. Using these isotopes, we can derive an age for each mineral grain based on the principle of radiometric decay. A histogram of ages here is shown on the bottom of this slide. So these numbers here are ages in millions of years, and these bars are part of a histogram showing for each bar how many zircons have that age. And what we can see from this pretty readily is that there's a peak in ages right there and another one right there, which is telling us that this sandstone, the source for the sandstone, had ages of about 3275 million years ago and 3450 million years ago, with some other ages scattered around those. Maybe that's a pretty good, well-defined peak. Maybe that one is too. And knowing this age distribution is really useful information because different parts of the Earth's crust consist of rocks of different ages. This can also kind of be ambiguous too, because the sandstone containing the zircons may have been directly derived from an igneous source with that age, or it could have been derived from an older sandstone, and then that sandstone may have been derived from igneous rocks of this age. So here's a plot from my own research. In my research, I dated over 4,000 individual zircons from dozens of samples in North China. And this plot here is an age spectrum of those samples. Each of the numbered peaks here is the most probable age of the source rock from which these zircons was derived. Now, how I constructed this plot was I took each individual age and its uncertainty, or error, and I drew that as a normal curve. So here has a wide error, here has a narrow error, and then here has an error in between. And if you take these three independent ages and you just add up these curves, then you get an age spectrum curve, a sum curve for all of these, A plus B plus C. And that's essentially all this is for 4,687 independent curves. Now, what this plot tells us is that all of the sandstones in North China consist of zircons with these main age groupings. And what that tells us is that the crust of North China consists of rock with those ages. So just by looking at the age spectrum of zircons and sandstones, you can tell a lot about the age of the continent that you're on. Okay, conversely, why bother doing this in any case? Well, why bother is because you'll often be surprised. And this is a good example of some surprising results that occurred with some rocks that were pretty well known. This area here, and this is a map of North America, is the area over which a geologic unit called the Navajo Sandstone was deposited. The Navajo Sandstone is an aeolian deposit, a wind-blown sand deposit. So that entire area outlined in red used to be a big sand sea, sort of like the Sahara. The wind was basically blowing from the north and west, the wind that deposited all of that sand. And we know that just by looking at the crossbeds in the sandstone. It's pretty easy to discern the current direction. So you'd expect that the source for all of the sand in these ancient dunes was probably up towards the northwest. Well, if you look at the geologic province ages for North America, you find that northwest of the Navajo Sandstone is some of the youngest rock that you have in North America. All of the older rocks occur further to the east. Well, it turns out that the Navajo Sandstone is chock full of zircons from this terrain called the Grenville. And those zircons, ranging in age from half a billion to 1 billion years, those zircons must have gotten from here all the way out to where the Navajo Sandstone is out there somehow, and since the wind was blowing from the northwest, it wasn't the wind that brought it there. And so the running hypothesis is that all of those zircons were transported by some major river system that then deposited the sands up here where they were picked up by the wind and carried down into our Navajo Sandstone Basin. And this is something that we never would have known without zircons. So it's an interesting piece of information. Okay, well, mudstone provenance is a little bit more obscure. Mud contains clay minerals, of which there are four main types. All of these clay minerals are sheet silicates, which consist of two main types of layers. A tetrahedral layer, basically a silica or alumina tetrahedra, and then an octahedral layer consisting of aluminum hydroxide. The tetrahedral and octahedral layers are symbolized by T and O in the diagrams for each of these types of clays. So these layers, tetrahedral and octahedral, are stacked differently in different types of clay mineral. So kaolinite is the first of these. Kaolinite is a 1-to-1 clay, meaning that each layer or each sheet in the clay mineral consists of an equal amount of tetrahedral and octahedral layers, TO, 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 stacked on top of each other. Smectite and all the rest of these clay types are instead 1-to-2 clays. In other words, they consist of a tetrahedral layer, an octahedral layer, and a tetrahedral layer, basically forming a sandwich with the octahedral layer being in between two tetrahedral layers. Well, this arrangement of tetrahedral and octahedral layers leaves some residual charge on this structure, and so you need to have some sort of ions or polar material in between this layer and the one beneath it in order for that clay mineral to be charge balanced and to hold together. So all of these other three types of clays, smectite, illite, and chlorite, are 1-to-2 clays, and the only reason that they differ really is because of different material in these layers, different cations, and different interlayer cations bonding the things together. So smectite has sodium and calcium, illite has potassium, chlorite's got aluminum, magnesium, and iron in between. between the TOT layers. You may recall that kaolinite is the product of feldspar weathering in humid and tropical environments. So when you weather feldspar, you leave behind some residual silica to form the tetrahedral layers and some residual aluminum hydroxide to form the octahedral layers, and those bond together to make a new clay called kaolinite. In conditions where weathering and leaching is incomplete, you might leave behind some of the cations from the feldspar, and you might leave behind a lot of excess silica as well because you're not as effectively leaching those away from the feldspar due to weathering. And in that case, what you get is you get a smectite. A smectite is a clay that's got a lot more silica in the tetrahedral layers and has interlayer cations that are the cations present in feldspar. So what you get when you get what happens to get a smectite is you have incomplete weathering of feldspars. The cations and the silica are not washed away in solution. They stick behind and they form a smectite clay. Illite is the product of either weathering of K-spar or it's the product of collapse of smectite. So it turns out when you bury and heat up smectite, smectite releases the water from the interlayers and it tightens up its structure a little bit. Those two layers get closer together and the sodium and calcium get replaced by potassium. So illite's basically a product of the diagenesis or burial of smectite. Chlorite is the only of these is produced mainly in metamorphic rocks. It can also occur as a cement or a matrix in sedimentary rocks that have been buried deeply, but it needs high heat to form. So chlorite is not a product of weathering at the surface. Instead, it's a clay mineral that forms during metamorphism or deep burial of sediments. Okay, well, we can use the relative proportions of these minerals to say something about the environment from which they came. So kaolinite forms in tropical soils, and if you look at the modern day oceans, kaolinite largely is found in deep sea sediments, only near the tropics where winds or whatever else blow or rivers deliver that kaolinite to the ocean basins at those latitudes. So you'll find kaolinite soils and kaolinite in seafloor sediments only in the tropics. Illite is detrital. Illite is derived from older mudstone. Remember, illite is a diagenetic product, a byproduct of smectite. And so you'll tend to find a lot of illite wherever weathering rates are a little bit lower because you're basically getting that illite from the weathering of old rocks, sedimentary rocks on the continents, and then that gets delivered to the oceans. But you're not getting a lot of kaolinite like you would in a tropical setting. Finally, chlorite is detrital and derived from older rocks, and wherever you see a lot of chlorite, you need to have weathering rates that are exceedingly low. And the reason for that is that chlorite itself will weather over time to illite, or maybe to smectite, depending on the weathering regime. And so if you see a lot of chlorite in seafloor sediments, you've got to have the lowest weathering rates in the world, and that's why you see chlorite only near polar regions where there's virtually no weathering at all because everything's iced over, and you're delivering just fragments of chlorite from the rocks that already existed and have been ground down by glaciers. Clay minerals also vary in proportion over time. So this is the geologic time scale here, going from Precambrian through Paleozoic, Mesozoic, Cenozoic, and up to the modern day. And what you find is that the proportion of smectite over geologic time decreases as you go back in time, and the proportion of illite increases as you go back in time. And this just simply reflects the fact that smectite, when it's buried, and especially when it's buried deeply, converts to illite. And And so the older rocks, which have been buried more deeply for longer, it stands to reason that they would consist of more illite than smectite because this is converting to this. Okay, so we've covered pretty much all I will have to say about detrital rocks and what they can tell you about source. Thank you for listening.